Hello again, National 5. Today we're going to be looking at equivalent dose rate and also at background radiation. So hopefully by the end of this we'll be able to use the relationship to solve problems involving equivalent dose rate, equivalent dose and time, and we'll also have some knowledge of the equivalent dose rate and exposure safety limits for the public and workers in the UK. So equivalent dose rate, that is the equivalent dose per time. It's a rate, so it's calculated over a certain amount of time, and it's calculated using the equation here, h dot equals h over t. So that's the equivalent dose rate is h dot, and it's in sieverts per time, whatever your time is. If it's seconds, it'll be sieverts per second. If your time is in minutes, it'll be sieverts per minute, etc. H there, as usual, is your equivalent dose in sieverts, and t is your time, and it could be in seconds, minutes, hours, years, etc. You might want to pause the video here and just take a note of that, it's quite important. So a worked example using that, we've got a worker in a nuclear power plant who's exposed to 10 milligrays of slow neutron radiation in 1 year. What is the equivalent dose per second that the worker absorbs? So the equivalent dose here, we've got our H equals D times WR. So again, using the table that we had before, 10 milligrays is 0.01 grays, and the radiation weighting factor for slow neutrons is 3. So we've got 0.03 sieverts. We know that it's over 1 year, but we want it in sieverts per second, so we need to convert 1 year into seconds. So we have 60 times 60 times 24 times 365 to get the number of seconds in a year. And then we use our equivalent dose rate equation, h dot equals h over t. Pop our numbers in, 0.03 divided by 31,536,000, and that gives us 9.5 times 10 to the negative 10 sieverts per second. Another example, this time we want to know how long it would take to reach the annual UK safety limit for the general public, which is 1 millisievert, when exposed to 6 microsieverts per minute. So use our equation again, h dot equals h over t. Pop in our numbers, remember microsievert, so that's times 10 to the negative 6. So 6 times 10 to the negative 6 equals 1 times 10 to the negative 3, because it's 1 millisievert divided by time. Rearrange for time there, and we get 167 minutes. So I spoke briefly there about UK safety limits. There are limits that are imposed by the government on how much radiation we can be exposed to every year. So the average annual background radiation in the UK is about 2.2 millisieverts. Of course, this depends on where in the UK you are, but that is the average. The annual effective dose limit for a member of the public is 1 millisievert, and for a radiation worker it's 20 millisieverts. Now these limits for the public and for a radiation worker, they're on top of that annual background radiation. So in total, you could be exposed to 3.2 millisieverts in 1 year. One thing we need to know as well is where this background radiation comes from. And it's a mixture of both natural sources and artificial sources. So some of the natural sources include cosmic rays, which is just radiation from space, radon gas that's trapped in the earth, from rocks and buildings all around us emit some radiation, and also from our food and drink. Bananas have some radioactive potassium in them, again not enough to cause harm, but it all adds up to this background radiation. Some of the artificial sources, medical sources and dental x-rays, things like that, in medical diagnosis and treatment, some radioactive fallout from nuclear weapons testing, radioactive waste from nuclear power stations, and some industrial and consumer use of radiation, such as in your smoke detectors and sterilization of equipment and things like that. Again, important that you know some of these natural sources and artificial sources, so you might want to pause again here and take a note of that. And this graphic just shows again a bit of a breakdown of the proportions of those background radiation sources. From this we can see that most of it is this natural radiation that comes around us, whereas a small fraction is actually our artificial sources, An even smaller fraction there we can see is actually nuclear power and weapons tests.